From this information, we'll be able to conclude which wheel is the most.
Use this information to conclude, given a suitable area,
which represent no spoiler. Second spoiler is a lip spoiler there.
As this would affect the accuracy of the results. Conclusions are drawn, which allows us to recommend a specific helmet. Drag consists of pressure drag and viscous drag. For the blue helmet, both of these drags will be higher than the rest of the helmet, increasing overall drag, which fits with the results. It has a highest drag at 5.81 meters for the average speed of 25.9 meters per second. Drag also increases with the increase of surface area. As the blue area has the most surface area, it therefore has the highest drag. Blue helmet has vents, which adds to the high level of breathability. It swirls air around the head, creating turbulence, and this is ideal for those competing in Tour de France, as they often get heat stress, and the vents will allow heat to be able to escape, therefore.
By a universal dynamometer. The motor circulates water through the machine and into the pressure valves, which allow us to change the water pressure flowing through. This is where our 3D printed turbines will go, and to induce a power from these turbines, we must adjust the torque using this torque dynamometer.
So as a group, we aim to answer the research question: how can changing the angle of the propeller turbine blades found at a hydroelectric dam make the renewable energy source more efficient when producing energy?
In our experiment, we're looking for two things: the turbine efficiency from our 3D printed turbines, as well as the power they generate. Now, to figure out the turbine efficiency is very simple. It's using the turbine shaft power multiplied by the hydraulic power at the turbine, then times by 100.
As a group, we quickly came to the decision that we wanted to test an object in the wind tunnel, and what better idea is there apart from bullets. Their whole Their whole principle is their aerodynamic shape. We want to experiment with this. We want to find the ideal shape for a long-distance firearm. Our predictions were that the pointed tip with a boat tail would have the least drag. We also predicted that a boat tail compared to a flat base would have less drag, as their drag coefficient showed this. These predictions were made with the ballistics coefficient equation. A pointed tip compared to a rounded tip would give a higher ballistic coefficient value, and a higher ballistic coefficient value would give a bullet a more stable flight with better accuracy and range.
When the bullets were created on CAD, they included a 4mm hole that was machined to 6mm, and then the holes were threaded so the bullets could be fastened onto them, mounting rod. The mounting rod is tied to these holes with the angular The models were secured horizontally by the use of a 90-degree key.
So for our thermofluids project, we chose to do water hammer suppression. So water hammer describes the pressure changes that are associated. One common option is the use of an expansion chamber. That's going to provide more space for the pressure to have time to reduce. Another option, slowing the rate at which the valve is closing. That close moving. What are some of the difficulties we faced while undergoing the project?
So one of the first difficulties we had was recording the pressure. We went for an analog pressure sensor because the water hammer.
Beginning of the experiment as a collective, we decided to predict the outcome that we expected to see from using pipes bent to a 45 and 90 degree angle and measuring the overall resultant force applied on the pipes when a high pressure stream is put through them. We all agreed that we would expect to see a greater resultant force from the pipe with the 90 degree bend due to the water having to travel around a larger bend in the pipe. We predicted this by simply thinking about the momentum of the water before, during and after entering the system. As the water enters the pipe, it will have a forward momentum that depends on the flow rate which we set. When the water enters the pipe, it travels up the pipe as normal until it reaches the bent section, at which the water still has a vertical momentum. As it travels around the bend in the system, this results in the water pushing up on the inside of the pipe, causing an overall effect on the system.
We designed a way to join the pipes directly above the jet nozzle. This would make sure that all the water would flow into the pipe and not get misdirected, giving us an inaccurate reading.
The 90 degree pipe had a much larger force on it than the 45 degree pipe because the water is hitting a sharper bend, so more force is acting upwards. Overall, the results were lower than we predicted. This is most likely due to the longer curve of the pipe compared to a flat plate.
Don't understand it. Or is that an optical illusion, the effect of it looking like it's doing that? What do you think?
And convert it into electrical energy. The way that works is that the energy from the water is used to spin blades within the turbine, which then sets off a generator which spins to transfer the kinetic energy to electrical. However, the experiment itself is not 100% efficient. There is a loss of energy within the process due to numerous factors.
Stroboscope to check how fast is the turbine spinning.
The pressure drag is high and the viscosity drag is low, giving a low efficiency. And at salted water, the pressure drag is low and viscosity drag is high, giving also low efficiency. In order to optimize the efficiency of the turbine, both drags should be compromised. Depending on the turbine, one or the other drag should have more impact.
Different spoilers affect the performance of the car. This is the subsonic wind tunnel that we used for our experiment. We made sure that the angle was at 0 degrees for our car. We mounted our car with the different spoilers on this rod, and then we inserted it into the test area and made sure that it was at a 0 degree angle.
Hey you! Cash into cash every single time.
And now, on to the scientists.
So, after much hard work and much deliberation, we've decided that three darts are going to be most beneficial to test for our project.
And here, the scientists are hard at work testing and running simulations on the flights, making sure they find out which design is the best to put on a dart.
Which I like to call the underbird, actually had the most amount of drag, and like Martin said, the joint most lift as well. So that actually means that we feel like it was the most stable.
The materials were then placed as close to the heat as possible, which was 10 centimetres, and the sensor was just behind at 5 centimetres behind that. Each of the materials was also placed between two metal slides with holes in the centre. This allowed for the same amount of material to be exposed to the heat, which was important, since some of our samples vary in size. We then decided, in order to keep the experiment fair, we would put each of the materials in front of the source for the same amount of time in order to try and keep the experiment as fair as possible. After a test run, we decided that 2 minutes gave enough time for each material.
These are the results we gathered, showing the irradiance values at the heat flux sensor and what materials were, distance from source and temperature at source.
flow into a turbulent flow. As such, our research question is as follows. What is it that determines the transition period of the flow of a liquid inside a sealed container, such as the laminar flow hood? To demonstrate this, we'll be using the following experiment. We will now consider what it is that determines whether or not flow is either laminar or turbulent. First of all, we know that the laminar flow is a result of inertial forces within the tube given by the liquid. We also know that turbulent flow is given by the viscous forces within the liquid. It was Reynolds who first came up with this idea and realised that he could create an arbitrary unit, dimensionless, which would also, for any given liquid, that would describe whether or not the flow at a given flow rate was turbulent or laminar. First of all, let's consider
So we are investigating how the number of blades affect
that has the best efficiency for the centrifugal pump. We have made them by 3D printing them. We believe that the one with the least amount of blades will have the best efficiency because there is less resistance to the flow of water.
Machine times by the volumetric flow rate.
Converted times them by 100,000 pascals. So that's what the equation is working in. Shaft power, we also got it from the diameter and came as it works.
How the volumetric flow rate.
Today we'll be doing an investigation. We've got 4 different size spoilers and we'll be seeing whether the bigger the contact area of a spoiler, the bigger the downforce.
We believe our experiment will be successful. The wind speed will generally be slower than that of a real car, and the size of the car will be proportionate of that of the real life car.
We'll be testing to see how each spoiler varies in Reynolds number and drag coefficient to show which spoiler produces the most downforce.
Okay, so in this experiment we will be trying to find out the Reynolds number for each of the spoilers.
For this, we times the density by the velocity by the chord length, all divided by the dynamic viscosity.
For the known values that we've got the dynamic viscosity of being
1.5 times 10 to the minus 5 Pascal seconds.
The velocity being 30 meters per second and the density being 1.225 kilogram per meter cubed. We've got four chord lengths, and with each of these 4 chord lengths we'll be working out these Reynolds numbers here. So if we've got a chord length of 0.02 meters, we should have a Reynolds number of 4.9 times 10 to the 4. With a chord length of 0.008 meters, we should have a Reynolds number of 1.96 times 10 to the 4. With a chord length of 0.0125 meters, we should have 3.06 times 10 to the 4. And with a chord length of 0.0121 meters, we should have a Reynolds number of 2.96 times 10 to the 4.